Hello, welcome. I am Matt Koulakondis. This is designing a fast, efficient, cache-friendly hash table, step by step. If you thought it was something else, stay. This is better than what you thought it would be, trust me. But before I start, I just want to give credit, because this is the work of a lot of people. I am not the primary author of many of this. I'm more the primary evangelist. I convince people to do things, and they listen to me because they're fools. So in alphabetical order, I want to thank Alkis Evlogimenos, who is probably the most primary author for all of this. He has done the lion's share of the coding and much of the deep thought involved. Jeff Dean from Google came in with some brilliant insights at a very opportune moment. Jeffrey Lim, also everyone's at Google, Jeffrey Lim did a bit of the very micro optimization of assembly. None of his work is actually going to be covered because it's way too low level. Roman Paraplitsa is responsible for all of the crazy template hackery. Sam Benza also did a huge volume of the code reviews, the template hackery, some of the optimization work, and has just sort of generally spread himself across all of it effectively. Sanjay Gemwat came in with Jeff Dean at the same moment, provided a very key observation. If you don't know Sanjay and Jeff Dean, they're sort of like a single hive mind that walks around in two bodies. Vitaly Goldstein did a bunch of work around the hash functions and is still doing it. So this is a massive team effort, and it would be arrogant of me in the extreme, more arrogant than I typically present, to not cite them in it. So as I said, we're designing cache tables step by step. You've probably seen this sort of talk before, right? I start with something simple. No, this is a talk in C++. I start with something simple, and then I'm just going to blow past it to something complicated much faster than you can follow. That's how these talks work. It's always how step-by-step talks work. I'm sorry, it was in my contract. Let me give you a few words of warning, though. For the purposes of this talk, table, map, and set are interchangeable words. If I had more practice, I would always say table, but I'm bad at that, and I'm just going to throw map and set in there to confuse you, because I like doing that. What I say, I am aiming for 90% true. Perfect fidelity interferes with understanding when you are dealing with a topic this complicated, right? 90% true. A huge amount of the performance of a hash table depends on the quality of your hash functions. There are doctoral theses about this, and I'm going to gloss over all of it. I'm just going to assume that we have a good hash function for whatever definition of good I want. I will try to call out the spots where it matters the most, but I'll miss some, and you should just know you have a good hash function. The interaction between hash functions and hash tables is very subtle and often depends on the exact implementation of the table. A little bit of background, right? Hash tables are incredibly performance sensitive. At Google, right now, as I am speaking, in our fleet, 1% of the CPUs are computing something inside a hash table. As I am speaking, more than 4% of Google's RAM is owned by a hash table. And that's just in C++. I don't know how to get the numbers for Java, right? At these scales, there is no trade-off, none, that is correct for all users. When we talk about cache tables, you have to talk about whether a table is cold or hot. Does the entire table fit in L1 cache? If it does, then you should be counting instructions. If everything's in L1 cache, it's all about how many instructions are executed. If everything's cold, all you really need to talk about are L1 cache misses. Everything else comes for free. As with anything like this, benchmarks are the only source of truth you will ever get, and they are lies, every last one of them. You can find a lot of blog posts about, like, I made the fastest hash table ever, and here's my one benchmark to prove it. Anytime someone comes to you with one benchmark, they have gamed that benchmark. Sorry. So Google's a big code base. We talk about it a lot. Trust me, it's really big. Hiram's law, and Titus has told me this slide is obligatory, is a very real thing at Google, right? For those of you that don't know, Hiram's law says, if there's anything a user can observe about the implementation of your API, they will rely upon it, given enough users. And this is the bane of the janitor's existence. This is the bane of the CPP standard's existence. Right? So what can we look at Google's code base and figure out? We're still in the world of background, sorry. I know there's a lot. Nobody erases, except for the people who do. Only two operations really matter: insert and find, except for the people who need efficient table scans. That's just iterating over the whole table. Nobody uses the bucket interface. I'll define that in a moment, but nobody. And like, there's no Hiram's law exception here. Literally nobody. There was one use of it in Google 3, and it's a debug API. Nobody uses load factor correctly. I audited every user of load factor in Google 3. They were all wrong. All of them. Right, so with that covered, enough warnings and context, I'm going to introduce to you the new hash table at Google called Swiss table. It is the fastest hash table in the world with no caveats, ifs, ands, or buts. It's the best in all situations. OK, a couple people got that it was a joke. So let's start with unordered map, unordered set, right? This is our starting point. You're going to see diagrams like this a lot, so let me walk you through what the parts of this diagram are. Right? The H, that's your hash code. It is 64 bits in all of its glorious splendor. I don't care about 32-bit platforms. If you're on a 32-bit platform, just whenever I say 64, make some mental adjustments. It's fine. Technically, this is optional, but it's usually there, so I'm going to include it. This is the actual value. This is the thing that we want to store. Because the value is in a separate allocation, we say that it has pointer stability. No matter what happens to the internals of your hash table, the value doesn't move. This is a property guaranteed by the standard. That is the symbol for a null pointer. I know. It's awesome, isn't it? This is used to indicate the end of linked lists. So these values are in the same bucket. I mentioned the bucket API, right? When you take the hash, you mod by the table size, and then you end up with a bucket. And that bucket chain is all of the values that land in that bucket. Load factor is how many things are in your table versus how many slots do you have? What is your bucket count? For this beautiful table, 60%. Tables use the load factor to decide when they want to grow. So back to where we were. This is our starting point, stood unordered set. This is 90% true. I wonder if we can make this a little more true. Yeah, it really does look like that. And I know you're sitting there going, whoa. But there's a trick to dealing with the standard. You slow down, take a deep breath, and just lie back and think, oh, now it makes sense. Yeah, STL's starting to make sense, and that is never a good sign. But this picture is more true. Oh, I should mention, whenever I'm talking about the standard, I am talking about libstud C++ 4.9, 4.8, something around there. Yeah, I know it's old. Don't judge me. I don't choose that, and upgrading is a pain. But what can we learn from this picture, right? We store the hash and the pointer. That's an extra 16 bytes per entry. And I can hear you saying, like, 16 bytes? That's like practically free. Who cares? Turns out that is somewhere between 0.1 and 0.2% of fleet-wide RAM at Google. Did I mention that hash tables are used a lot? When we iterate across this thing, we actually end up just walking this linked list. It's O of size. It's kind of a random thing for me to mention here. We're just going to put a pin in that. We'll come back to it later. Okay? The iteration order for this container is reproducible for any given insertion order. Hiram will rear his actually fairly attractive head at some point later. But let's look at how find on this table operates in action. We want to find this element. It happens to be the second one in our bucket chain, right? We compute the hash to figure out where we're going. We follow that to the entry before the first entry in our bucket chain. So we always just skip this one. Then we look at the first entry that's actually there. We compare our computed hash against the hash stored in that thing. If that matches, then we compare the value against the value that we want. And then we skip because it didn't match, and we get to the one we actually wanted. 4 different memory accesses to find that element. It's kind of stinky. I'm trying to tone down my language. I'm sorry. I worked on ships for a while. It has left me with a foul mouth. If a few expletives slip out, please forgive me. Back to our simplified view. Here we are. But let's improve it just a little bit with what we learned from our deeper dive. There's a dummy node. Yeah, it's there. Why is it there? Well, in order to insert into a singly linked list, you need to have the element before so that you can slice it in appropriately. Now, you could say, why don't we just put it at the end of the singly linked list? But then you have to iterate to the end of your bucket chain to insert a new item on that bucket chain, and that was just a thing they decided was an unacceptable compromise. I didn't design it. I don't know. So what could we do about this? Well, we can make a doubly linked list, right? Then we can insert without it. We don't need that extra dummy slot. But that adds another 8 bytes to everything. And that's another 0.1% of fleet-wide RAM. And most of the reason I started this was to save RAM. Also, it fluffs out our L1 caches, which makes us feel bad about ourselves, and the whole thing sounds expensive, so let's not do that. What if we could make this more like our original picture, right? What if we just try and return it to our mental model? This is not an awful idea. It looks simpler. Coincidentally, this is what GNU CXX hash map actually looks like. What do we gain when we do this? We eliminate a memory indirection on find and insert. By the way, this, what do we gain? What do we lose? It's going to come up a lot. This is how you need to think when you are optimizing a data structure. So what do we gain? We've lost a memory indirection. What do we lose? Iteration requires scanning not just across our buckets, but across the entire array. So now iteration is not O of size, it's O of capacity plus O of size. And I can hear the theoreticians among you saying, well, capacity is bounded by max load factor over 2 and max load factor, which is a constant, and therefore it's O of size. And you would be correct, except for the people who reuse their tables. They grow it out to 1 million elements because they have some request that needs 1 million things, then they call clear, and then they insert 7 elements, and then they iterate over it. Ask me how I know about these people. Hiram's law strikes again. Right? Well, on the plus side, these people are the minority. We're kind of willing to lose them for now. Why are we paying for that hash, right? Maybe we can just drop the hash out of here and save ourselves a little bit. Felt good. I feel like I lost some weight. Do I look thinner? No? Maybe. So what did I lose when I did this? Now, when the table resizes, I need to recompute the hash, which is potentially expensive because I have to call the hash function on every element already in the table. But is that expensive? It depends on the type. If it's an int or a double, no. Actually, computing the hash function is basically free. If it's a big complicated type, yeah, it is expensive. It's a trade-off. I hear trade-offs are a thing. Now, when we're trying to run find, we might have to run EQ more often because we can't fast path out by comparing the hashes. Is that expensive? It depends on the type. If your quality is expensive to compute, like a string, it could be expensive. But if your quality is cheap to compute, because it's like an int or a double or something, no, and we got rid of a branch. Trade-offs. On the plus side, users can get this back if they want. They can put in a type that caches its own hash value. So we didn't technically lose any power. We may have lost some convenience. What did we gain? About 0.1% of fleet-wide RAM. I know. Also, the vague feeling of superiority when we force a difficult decision onto the user. And that is the C++ way. So maybe I can do it again, right? What if I remove the pointers? What did I just do? This isn't even a chaining hash table anymore. This is a probing table. This is madness. Or is it? Sure, probing has an entire rich field of academic depth to it that we're not going to go into. But what did we gain? Another 0.1% of fleet-wide RAM. It's kind of awesome. What did I lose? Well, if I iterate over the buckets for a given thing, it becomes a lot more complicated. But the good news is, nobody uses the bucket interface. Literally, nobody. Not even Hiram. It's amazing. Why don't we try and see how find works, right? We're looking for the same element again. We'll do our thing. We compute the hash, we go to the spot. We jump to the first thing, the value doesn't match. We probe to the next one, and then we found it. It's worth noting that this probe is free because it's right next to the first piece in memory. Our cache fetch pulled it in, no extra cost for that. So here we are, only 3 memory accesses instead of 4. But I hear sort of susurrations of concern. What about erasing elements? Won't this affect our bucket chain in some way? And the answer is yes. We just add sentinels. You have a little dead marker that says, this is a tombstone. When you're probing for a find or an insert, you can't stop just because you found an empty thing. Well, you can't stop when you find a deleted element. You have to stop when you find an empty element. And then you might be thinking, well, how do tombstones interact with load factor? Because load factor is trying to express this concept of how full your table is, which is really just trying to tell you how long your probe sequences are. And tombstones add to your load factor, so erase doesn't actually free up your load factor. It's kind of annoying, but nobody uses load factor correctly anyway. You might be asking, did we just break standards compatibility? Yes, multiple times. This code in the standard is guaranteed never to trigger a rehash. I'll give you a moment to read it while I drink some of this lovely, lovely Diet Mountain Dew. That was a joke for my friends. So this code will never trigger a rehash with stood unordered set. But with our new hash table, it can trigger a rehash. And I just don't feel bad about it. I've looked in Google. Nobody relies on this. Nobody. It turns out Hiram isn't quite as right as he thinks, but boy, is he nearly as right as he thinks. All right, let's give this guy a name. Node hash set. I like it. It has nodes. It's a hash set. And it also has this sort of weighty future portent. Why would I call it node hash set if I didn't have some other thing that could go there? Turns out I wrote the talk. I know where it's going. Yay. We've gone far enough without data, and I've been told that all talks need graphs. And rather than just a giraffe going up and to the right, I'm going to include a real one. But before I do that, let me talk about benchmarking. There are a whole space of benchmarks, right? You need to know, how full is your table? Did it just grow? Is it at its minimum occupancy? Or is it one element from growing? Is it at its maximum occupancy? Or is it somewhere in between? How does the memory interact with cache? Is your table just entirely an L1 cache and just super hot and ready to go? Or is your table so large that it's way out to RAM, it's not even in your L3 cache, like you see it kind of off in the distance, you're like, bye, honey. Oh. Yeah. What are you doing, right? If you're doing a find, did you actually find the element, or is the element not in the table? If you're doing an insert, is the element not on the table? Or is the insert succeeding? These are all sort of like, there's a giant space of these things. When we first wrote our benchmarks, the very first run took 3 days. And then we looked at that data and aggressively cut dimensionality. But without running the data once, how do you know what dimensions are inconsequential? Also, how large is the key that you're keeping in it? Are you keeping ints in your set? Or are you keeping massive structs that are like a meg each? Please don't keep massive structs that are like a meg each. Or use a node one that has an indirection. So, and I really need to stop saying so on slide transitions. I'm trying to fix it. I'm sorry, folks. It's a hard habit to break. I could go into a whole ton of variations on this graph, but it would take a big chunk of time and really wouldn't be that illuminating. What is this graph? This is stood unordered set versus node hash set. We are trying to find elements that are present in the graph. They are in the set. They are 4-byte elements. What's the biggest takeaway? 2x faster. Woo! That's awesome. Less RAM. It's also made of awesome. All the other graphs I would show you for this comparison are basically the same, and I have a place to be. So we're going to keep going from here. We have our node hash set. We got this far by removing data and indirections. Now we have a choice, right? If you take the red pill, we're going to leave the standard further behind. We're going to eliminate more indirections, and we're going to find all the performance we can. If you take the blue pill, we're going to play games hiding hash codes in like inappropriate places in our pointers, and leave the space of things that I have data on and start to speculate a lot more heavily. But before you decide, let me ask you a trick question. What's the first thing you reach for? A stood vector or a stood list? Yes, a vector. Why is unordered map any different? Like I said, it was a trick question. We just put the values right into it. We took the red pill, but what are those? Sentinels. Don't mind them. I'm sure you have 2 distinct entries for your value that you're never going to need to represent in your map, right? You just besides, look, right? 4 to 5 times better. Totally worth those sentinels. Also, I cheated. This hash table exists in the wild. It is called dense hash set. You can find multiple copies of it running around on the internet. Just search for it using Google. Somebody got the joke. It only has a couple small problems. It's a little bit old and crufty, so you're going to need to update it to the more modern APIs. It has to have those sentinels in it, and its performance degrades with the size of its keys. This is 4-byte keys versus 64-byte keys. And the performance goes down 80%-ish, almost 2x. Like, this is not pretty. You have your dense hash set somewhere, and it's some value you don't own, and somebody over there adds some entries into that struct, and all of a sudden your performance falls off a cliff. It's not a fun trade, right? We're going to table the size question for a moment and think about maybe we can get rid of the sentinels, because the sentinels are the biggest usability issue for dense hash set. All right, sentinels. I'm going to need a little bit more space. Give me a moment while I rearrange. Yeah, much better. Maybe if I just add a little bit of metadata instead of having sentinels, right? Everybody loves metadata. So what is this? We're going to keep a little parallel array of metadata. Dark secret, it's in the same allocation, but for the purposes of our talk, we can think of them as separate. And what do we need to keep in our metadata array? Well, we need to know whether it's empty, whether it's full, or whether it's deleted. 1.5 bits. That is slightly awkward. We could do something where like every 2 elements gets 3 bits, and something like the bookmarking gets really painful, and I always hear people talk about it, and I've never seen the code for it. Like, I would not ask someone to do that in an interview, so I don't want to do it right now. I kind of wish that someone way smarter than me would just like show up and then be like, oh, a wild Sanjay and Jeff Dean appear. That was really oddly convenient. What are they saying, in case you can't see? It's use a whole byte. Use a whole byte for the metadata for each element, and store 7 bits of hash code in the lowest part of it, so you can do one thing for saying, am I a sentinel? Empty or deleted, then appears in the next 7 bits. Or 0 means it's full, and I have 7 bits of hash code. By the way, this totally happened in real life. We were struggling with problems, and like Jeff Dean and Sanjay sent me an email out of nowhere. Now we have a 2-level hash table. H1 is 57 bits, and it tells us where to look in our backing array. H1 is what we take the modulus of when we're figuring out where to go. H2 gives us this little bit mask that has to appear in the control bytes. This is where your hash function starts to become important. If your hash function hides all its entropy in the first 7 bits, you're going to get a lot of H1 collisions. If your hash function puts none of its entropy in the first 7 bits, you're going to get a lot of H2 collisions. And any type of collision is bad. I'm just going to say that we need a hash function that distributes the bits well. I'm going to leave it at that, let you guys do a little bit of research on your own later. Such things exist. There's even ways to take a weak hash function and turn it into a strong hash function. All right. Things are going to get complicated really quickly now. We're right at that moment where the coconut is heading, the machete is heading towards your arm, and we're hoping it hits the coconut. So I'm going to give a few things names. Position 3 has 2 notional items. It has a control byte in the metadata and a slot that actually stores the value. I know, not that many names. Now let's look at what we are storing in the control byte. We have our sentinels all have high bit 1, and our full things all have high bit 0. You may ask what that extra K sentinel is, because I only mentioned empty, deleted, and full before. It's the thing that lets you stop scanning your metadata for a table scan. I'm going to mention it now, and we're never going to talk about it again. It's never happened. Here's our H1 and our H2. It's kind of obvious. It's not that complicated. What does find look like for this table? Quick show of hands. Who wants to read all the code on the slide? And who wants to see a picture of how it works? And then I'll go back and let you read the code on the slide. People who want to see a picture? People who want to read the code? Sorry, coders. Pictures have it. Once again, we're finding the second element in that bucket chain. But I'm going to need to zoom in because those control bytes are really small. If you're feeling awesome, you can count them. I made sure that 8 of them fit in one of the others. Here we are. We zoomed in on our control bytes. Right? So, first thing we do, compute where we're looking. There we are. Well, our H2 hash didn't match for this element, so we're going to keep going. Nope, that one's deleted. Keep going. Hey, third position in our control bytes matches, H2 anyway. Let's go check our value. Yes, got it. It's awesome. 2 memory accesses. Pretty sweet. So that's find. I'll give you a few moments, not minutes, to read the code. So it still does probing, but as you saw, most of the probing happens in the control bytes. And that means it all happens really dense in L1 cache. We can handle really large probe chains before we need to fetch another L1 cache line, which is kind of awesome. But I wonder if we can do something better. I kind of wish someone brilliant would just show up and, yeah, I know. It's lame to reuse the same joke, but it really did happen. Use SSE instructions. All right, these 2 guys are really smart. Let's just try out their idea and see how far this gets us. Here's some SSE instructions to give us a bit mask for it. Right? Couple machine instructions, everyone follows that instantly. Totes. right? I didn't spend like 3 weeks with AUKUS trying to understand this. You all got this. Fine, we'll go into it a little bit. Set1 EPI8 will initialize a 128-bit vector of 16 8-bit things. It's just splatting it out again. It's pretty simple. Compare EQ, EPI8, takes two 128-bit things, and it gives you masks of 0 or FF where the bytes line up. Also pretty simple. It turns out most assembly instructions are pretty simple. It's just when you like combine them really densely in code with a lot of underscores that your eyes start to bleed and you're like, why did I do this? So there we are, CMP EQ EPI8. Move mask EPI8 takes our big 128-bit thing and just squishes it. Takes the high bit of each byte and gives us a 16-bit thing that has zeros where they didn't match and ones where they do match. Also known as a bit mask, telling us which of our 16 control bytes had the proper H2 hash. So if we put these instructions together, we get this nice thing that says, given an H2, give me the bit mask for everyone that matched. It's kind of awesome, and it's like 3 instructions. You get like 16 probe length and 3 instructions. It's amazing. Like I said, Sanjay and Jeff Dean are brilliant. All right, it's time to name a few more things. You can always tell when things are about to get complicated because I start naming them. I'm pretty sure there's like a theory of postmodernism about this. Did I hear a vague concern or susurration? No, great. So I'm gonna call a group of 16 of these things, right? 16 control bytes and 16 slots is a group. And our table is gonna contain n groups. It does mean our table will have a size of n times 16, but like, who cares? You never really wanted an exact size from your table. What you wanted was that sweet, sweet performance. Now that I have these names nailed down, let's look at how find is implemented. All right, I'm not gonna poll the audience again. I'm just gonna do the pictures and then come back to the code. Here we are, we're about to do our find. Step 1, look at all of them in parallel. Step 2, jump to the matching element. It's awesome. It's okay if you're wowed by this, I still am. It really does, it's crazy. Here we are, looking at find. I'm gonna let you read the code for a bit while I drink this sweet, sweet Diet Mountain Dew. Now's the moment where we should make some brilliant observations about this code. This equality operator is almost always true. By the time we've gotten to this equality operator, we know that H1 mod our table size is a match for this hash code. We know that H2 is a match for this hash code. We've compared a lot more bits of our hash code than a traditional table would. So this is always true, and we can just tell our compiler that. Predict true. I didn't put it in the slide because it's big, it's long, it's ugly, and it's in all caps. Caps scare people. True story. This branch says whether we need to probe to the next group. We only need to probe to the next group if the entire group of 16 elements is full. And that basically doesn't happen. If you have a perfectly distributed hash table, which I know doesn't exist, but work with me here. If you have a perfectly distributed hash table, you have to have a load factor greater than 94% before this if can ever be false. It's pretty good that way. So we can also give the compiler a hint about that one. Erase also gets a little bit of benefit from this fact. Now, when you're erasing an element, if any other element in the group was empty, you don't have to put a tombstone in. You can just set it back to empty, which means you don't need to hurt your load factor, and then all your finds are more likely to never need that branch. It's just like win-win. I'm still blown away by these things. Let's look at a little bit of graphs, right? I know there are a lot of graphs because if you don't have only one graph, it's hard to read, right? The red is stood unordered set. For those of you who are colorblind, that is the top line in all graphs. The blue is dense hash set. The green is our new thing, flat hash set. The left column is small payloads. These are 4-byte payloads. The right column is 64-byte payloads. The top is when you are finding an element that is in the table. The bottom is when you are finding an element that is not in the table. So what conclusions can we draw from this? We are crushing stood unordered set just across the board. It's awesome. We actually crush dense hash set most of the time. The one exception is if you have 4-byte items in your dense hash set and you're looking for things that are in your dense hash set, it's faster, just a little bit. Turns out, like, when your values are 4 bytes, the 1 byte you spend on metadata for probing is kind of expensive as a ratio of these things, and the fact that you have reduced probe chains doesn't quite win out over the extra cache miss. But you'll notice, one of the things this table does really nicely, if your elements aren't in the set, you don't even go to the values. You stay right in the metadata, most of the time. All right. Yeah. Now is when the talk takes a slight left turn. For those of you who don't recognize the reference, this is the Monty Python, and now for something completely different. Thus far, everything I've explained to you is about algorithmics, right? How do we get the algorithmic choices for a hash table better? Certainly some of them are just by constant factors, but they're still algorithmic choices. Let's think about the ergonomics of our containers for a moment. And don't worry, stood unordered map was built with all the loving care of stood vector of bool. Right? Stood vector of bool. We all knew it. I'm going to show you some code. We're going to play a little game. People just like throw up a hand when they realize what bear trap they're standing in. We got the fast person. I like that. But I'm going to wait just a little bit more. Oh, I see a few more popping up. Yep. That's right. Your const char star key is being created as a temp string in that find call. It is, of course, 2x slower. Heterogeneous lookup would fix this, but stood unordered set and map don't get heterogeneous lookup. They do for our containers, because we love the user. This one is a little bit harder, although someone at a talk I was at earlier actually identified it. That is the fastest anyone has gotten this. I had to get Alkis to explain this one to me over like 10 minutes on IM. It turns out that because you don't have a const on your P, your insert is going to the ref overload and not the const ref overload, and thus you are making a copy when you thought you were doing all the right things. It's C++. Really? How about this one? Anyone see what they did wrong this time? Yep. Naturally, calling in place will new a node on the heap, then try and do the in place and realize, oh, I already have this in the container, and then free that node from the heap for you. Yeah. And don't forget the const down here, or you're back in the previous bear trap. These are all variants on a theme. It turns out we can avoid constructing these temporary objects if we do something reasonably clever with templates. It turns out we can, and it's simple enough to fit on one slide. It doesn't fit well, and it kind of makes my brain hurt. This little trick allows us to avoid a ton of extra copies and some common pitfalls. Roughly, what this bit of magic does is it grovels through the arguments you were passed, and it tries really hard to see their true nature. And once it has seen the Platonic ideal of the arguments that you have passed, it uses that to look at the hash code instead of being like, well, man, he asked to in place, so I gotta allocate a node right now and then grovel through it. It does work. Please don't ask me how. Roman is the person you need to ask how. Fortunately, he's not here. All right, we're switching a little bit. This one is a little bit harder. You're going to need to know some of the internals of dense hash map. Your first hint, anyone want a hint, or do you want to keep staring? All right. Your first hint is that it is a probing table. It is dense hash set. Your second hint is that stood hash for an int is the identity. Does anyone see it now? Remember when I talked about low-order bits and entropy? We're shifting left by 10 bits, so everything has the same low-order bits in its hash code, and it's 25 times slower. All you need to do to fix it is to give it a better hash function. Well, we made that a little better for you. We provide a better hash function by default. You're welcome. Had I watched Moana on the way to the plane here, had I actually done that, I totally would have put the "you're welcome" there, but retrospect. Wah, wah. All right. These things are all subtle. They interact really deeply with each other. The power of defaults is massive. We're not going to give you a button to just blow up the world on your first attempt. I mean, you can do it in more advanced attempts, but like, we try really hard to make it, to give you affordances that make these things usable. We've even begun rolling out these across all of Google. We are just sending changes to everybody's code in Google. It's like, hey, you have an unordered set. Switch you to this one. It's pretty awesome. What are we looking at? This is a percentage of fleet-wide CPU that is consumed by hash tables. This is a stacked graph. So what you want is, you want to notice that we're going down and to the right. That means we are using less fleet-wide CPU. It's about 0.5% of fleet-wide CPU has gone down from these migrations. And this is our live sampling profiler in prod. This is like God's truth as near as we can tell it. If you're wondering about the colors, the blue is stood unordered set, the red is dense hash set, the yellow is our new hash tables, and the green is GNU CXX hash map. But the thing to note is we're trying to replace them all, and we're getting some good wins in CPU. We're getting even better wins in performance. I should warn you, the axes changed. Right? This was 2.4 at the top. This is 6 at the top. We are saving little over 1%, ballpark 1% of fleet-wide RAM. These numbers are really big when you multiply by the size of Google. So I can hear the crowd murmuring to them like, wait, you're doing a rollout, but you've also said that there are experiments in the works. How are you doing this without Hiram like coming and beating down your door? You can't make substantive changes. Hiram will stop you. The answer is careful defense. Anyone guess what this returns? Close, yeah. Our hash seed has a little mix step in it. In debug, we actually really seed that hash with a random thing. In non-debug, we use address layout randomization to give us just a little bit of randomness. And that shift by 12, that's because we found out it works better. I've done some things I ain't proud of, and the things I am proud of is frankly disgusting. But it gives us randomization on our tables. And then when we figure out where to insert an element in the group, in debug, mod 13/6, or mod 13 is greater than 6, it's a kind of cute way to be like, flip a coin for me. I mean, it's almost a coin. So it's true 50.3% of the time. I'm pretty sure somebody is going to start using flat hash set to generate random bits. And then they're going to complain when I change the distribution. They were like, I was relying on that 50.3. Come on. I'm sure some of you are wondering, I read the program description, it said Swiss table, but like he hasn't said Swiss table more than once. Why is it called Swiss table? I don't understand. The answer is the primary developer, Alkus and Roman, are in the Zurich office. Closed hashing, abbreviated CH, is also the top-level domain for Switzerland. And Swiss efficiency has just like a good spot in the zeitgeist. But in the end, we decided to name it something more descriptive. But we still use the code name. There's that. All right, now I'm going to describe a few of the experiments that are actually ongoing with this. Our first experiment is instead of having our groups aligned at 16 boundaries, what if any offset into your thing can start a group? What does this get you? It gets you better probing. You have sort of more different windows you can probe in. It actually gets you better randomization. This will make the ASLR step of the randomization randomize your tables better in opt mode too. People love it when I do that to them. What does it require? What's the con for this? Now I need to have 16 elements at the end of my metadata that are the same as the 16 elements at the beginning of my metadata. I have to set those things in both places so that if I land in the second to last spot, I can scan 16 elements forward. So now insert requires us to write 2 control bytes in some cases. But what does it give us? It lets us raise the default max load factor from 7/8 to 15/16. And that is a lot of RAM. And we can raise the max load factor and be faster. It's amazing. So this experiment is probably going to land, well, I wouldn't be surprised if Sam landed it while I was talking just to spite me. This was a really fun experiment. It's kind of a failure in some ways, but I can't resist showing it because whenever I saw it, I was just like, so we're going to get rid of the concept of 16 sized groups, and we're going to have 7 sized groups. And instead of all the metadata being at the front, the metadata is going to be attached to the front of the group. So we have 7 pointers. Each pointer is going to be 8 bytes. And that gives us 8 more bytes for our metadata at the front of it. Of those, 7 of those bytes are going to be for 8-bit hash codes. We're now storing an 8-bit H2 instead of a 7-bit H2, which is nice because it just like nudges us toward better things. We now have 1 byte left over that's not storing hash codes. Of those, 7 of the bits in it will represent whether an entry is there or not. And finally, the last bit will tell us, has this group ever been full? Because that is the only question you need to know whether you should probe to the next group. And if you add those up, it's 64 bytes. And the hardware people in the room will think, oh man, that's an L1 cache line. This is really brilliant. And it is. And if you have 8-byte values, it is very slightly faster. But most of the time you don't have 8-byte values, and the cost of specializing both of them was a lot of code complexity that we didn't want to just embrace. But if I were implementing, a Python interpreter or like the core hash table in any kind of interpreted language that always forced me to have an indirection, that would be my go-to. So, questions? Please use the mics. If you don't use the mic and you aim a soliloquy at me, I have to repeat the soliloquy, and rather than do that, I'm just going to summarize it in the worst possible light for you. Don't be shy. I can take it.
So one obvious question is, are you guys planning to open source it in near future?
I hear Abseil's a thing. I'd keep my eye on Abseil.
So,
We're not going to commit to a timeline, but if I were a betting man, I would put money before the end of the year.
before the end of the year. Cool, yeah. Because recently I was trying to use Google Dance Map. It is still outperforming the unordered map for me still most of the time when the key size is small and
Yeah.
we are doing mostly lookups. But in the GitHub of the unordered map, Google Dance Map, I saw some issues which are not fixed. So the next question is, are you guys supporting this Google Dance Map now, and how reliable it is to use in the big projects?
The existing dense hash set and dense hash map, as it exists right now, is reliable. Many production services at Google use it. Are we supporting it? No. We can't be bothered. It's old and crufty. We have this new thing. We like it better.
Okay, but you are using the same dance map which is in the GitHub right now as an open source?
Similar.
Similar. Okay, thank you.
What is the resizing strategy of the table as a whole? And how do you compute the module operation with the unknown size, or is it known?
So the table grows when it goes above its max load factor. Because no one knows how to use max load factor correctly, the set max load factor method is a no-op. You're welcome. The table is a power of 2 size. We are experimenting with other sizes for fast modulus, but power of 2 is really nice because it lets you just do a bit mask to get the lowest bits. It's bad because if your hash function isn't good, like if your hash function hides all your entropy in the high bits, that bit mask like comes by and hurts you. We're also experimenting with doing the thing in the table to strengthen weak hash functions to make them strong. But that is a few extra instructions, so it's a trade-off. I hear trade-offs are a thing.
I just wanted to ask whether you know from how many like elements in the set is your map more effective than just linear searching? Like say for, I don't know, 4-byte values.
I don't know offhand. I know that because we do the full 16-byte scan in one assembly instruction, it's very competitive for most things. But if you just happen to know that, like, I have a vector of like 3 4-byte values, just like use an array and scan them. At Google, we have a thing called flat set or flat map, which is just, it's backed by a vector that's flat.
See.
I just wanted to point out that regarding the bits of entropy, you can actually use some type traits to abstract that. Rather than relying on fixed number, you just use the traits to give you that.
You can. It is complicated when you add the type traits to it, and then you tell people, oh, your hasher function has to have this thing in a magical place, and it's a little bit annoying, but yes, you can. It is one of the options we're exploring. But because the performance effect of getting your hash function wrong is so deleterious, it's often on the order of 30 times, we are leaning towards we will just make your hash good. It's a little bit of the ergonomics on it. There's no way this talk was so good that nobody else has questions. Yes, the clever man in the front row has observed that I will not talk about the elephant in the room.
I think earlier, unless I misheard, you said something about like Google 2 and Google 3.
Oh.
What the heck is that?
Sorry. Google's source control has gone through like some historical revisions. There was once upon a time it was SVN, and then it was Perforce, and then there's this in-house thing that we use, and we call it Google 3. It's just the third iteration of our source control system. It is the monorepo. All the times you hear other Google engineers talk about our monorepo with millions of lines of code, inside Google, we just call it Google 3.
Yeah, I mean, you were suggesting that there might be another solution for if you have a heavy delete load as well. Are you going to be giving examples of how to do that too, or?
So it is reasonably fast if you have a heavy delete load. It's not the very first thing we've optimized for. Our sort of rough priorities are find, then insert, then erase. If you pull in your giant thing and put in 1 million elements once because your query is large, and then you clear it and try and reuse it, on our clear call, we won't actually keep that full 1 million elements. We will drop you down to 128 elements on the first clear, because otherwise your table scan might go to hell. If you're like, no, I really wanted those million elements, you can call .erase begin end. That's your backdoor.
I was wondering if you guys benchmarked against anything else, because I mean, standard unordered maps sort of been known to be slow for many years now.
Yeah.
And I mean, the benchmarks only showed against your own previous hash table. So any other implementations? I mean, Robinhood hashing is super popular now in new hash tables.
So we actually did implement a Robinhood hash on top of the same thing, and it turns out all of the extra logic around it is more expensive. Like, the whole raison d'etre of Robinhood hashing is we can reduce the length of probe chains. But if you can just scan a longer probe chain for free, it doesn't matter. And so the cost of more metadata to count your offsets and to bump things back turns out to be a loss on Robinhood hashing. You'll also find a lot of blog posts about people who've written the fastest hash table in the world. And it turns out the difference between how much code you need to implement in order to get a benchmark and how much code you need to implement to have a useful map is way different. Like, we got the benchmarks, and then we spent months filling out the tables and adding enough tests and all of that stuff. So the short answer is, yeah, we did some experiments. We did our own Robinhood hash. It is possible our own Robinhood hash had performance bugs that we didn't notice, but it was, even in our experiments, the Robinhood hash we had was comparable, sometimes slower, sometimes faster than the existing dense hash set.
Hi, you mentioned that you had some ASM tricks as well. Were they beyond the intrinsics, or?
No, just the intrinsic. Right, what Jeff Lim's contributions were. Yeah. So there were those sorts of tricks. Much of it was Jeff Lim would look at the generated assembly, look at the code, look at the generated assembly, think real hard, tweak the code until it generated the assembly he wanted.
Got it.
You've used SSE on x86. What can you say about other platforms which don't have SSE?
It does support all platforms. On non-SSE platforms, we emulate these SSE instructions by using arithmetic on longs. They produce more false positives, but they are still correct. Your group size goes from 16 to 8 because you don't have 128-bit things, you have 64-bit things. But it does work. Chrome and Android have both expressed a great deal of interest in picking this up. And the only modern CPUs that don't have SSE instructions are actually just old phones.
Could you repeat that const pair problem? I admit I didn't quite pick that up.
Yeah, that's fair. So there are two overloads for insert. One of which will take a const pair, const key, comma, value reference, and one of which will take an R-value reference. If you hand it the local that is not const, you'll end up in the R-value reference overload, with a temporary being created.
Okay.
You might call it a bug in the standard. I would call it C++ loves you. I'm told the session is over.